All right, we are now recording. Let's get the slideshow set up from the current slide. And let's just go over, I wish everybody were here. They're not, just two of you. Both of you done the student course evaluations? Yes? Good. Sam? Huh? Please do those, please.
I don't know where to do it.
Huh?
I don't know where to do it.
Okay. Okay. Have you checked your Lawson email?
No, I don't check that.
Okay. You can go to the Lawson webpage. You know how to get there, right? Okay, when you go to the Lawson webpage, the main page of our homepage of our webpage, there's a series of blue tabs at the top of the page. Over near the right, there's one big gold tab that stands out, and it says, what is that? Quick Link. I think that's the name of it, Quick Links. Click on that one, okay? You'll get a whole big long menu. You have to scroll down, scroll down, scroll down. Mm-hmm. And when you see something that comes up like student surveys or something like that, or it may say Smart Eval, S-M-A-R-T-E-V-A-L, Smart Eval. One of those two, either student surveys or student course surveys or Smart Eval, something like that. When you see that, click on it, and then you can go to it and go from there. It'll have all the information there. Your login is your 7-digit Lawson ID card number. You know that? It's probably a 1, 2, something or another. If you don't know it, I can get it for you, I think. Yes.
Let me see if it's saved on my computer.
What's that?
Let me see if it's saved on my computer.
Is it what?
If it's saved on my computer.
Well, there it is if you need it. Got it? Oh, that's good. Okay. I'll put the rest of the things that I had of yours there. Okay. Now, we were talking about what we're doing, where we're at. Okay, have you done the student course evaluation?
No.
Okay, please do those. Okay, you know how to?
Yeah.
Okay, good.
Do we get a bonus?
Yes, you get to feel real good about yourself for doing it. Please do them. I believe in giving points for physics, not for giving points for doing what you're supposed to do. Okay. Okay, so please do those. All right. Where we left off last time, we're in chapter 21. We should finish that pretty quickly tonight. And then the lab for this is just the second page. I gave you sometime earlier a first page of a lab that I think it says, what was it? Lab 7 or something, 6. It says Lab 6, electromagnetic induction. It's just a paper lab. You use a book and get the answers. And then after the one tonight, I'll give you another page. It says experiment or Lab 7, whatever the title of this chapter, alternating current circuits in electromagnetic waves. So those are going to be those two single pages go to be one lab, and that's your last lab. And I'll also give you your last test, which will be your 10th test, I believe. So you should have had 9 already, but if you weren't here last week, you may not have you may have gotten all those from last week. Okay? So you should have, this will be the 10th test tonight. And you can turn that into me anytime. In fact, look at the things I gave you back. Now, the things that were done last week, I don't have those graded yet because I graded all weekend and got caught up on 3 classes, but I didn't get a couple papers done out of this class. So I've still got most of this class to go. So when we finish this chapter, I'll give you that last page of lab and also give you the page of the test, the last test, and then You can turn anything else in to me. You can turn any of that in tonight. I'll be here till 9:15. Tomorrow I'll be available from 7:45 in the morning until noon, or a little before noon. Then I'm giving a test from noon to 2, approximately. And then I'll be back in my office between 2 and 5:15. That's when I hope to get caught up on most of the grading I'm behind on now. Okay, then Wednesday, I'm here from 7:45 in the morning until 9:15 at night. So anytime you want to bring it in, I'll probably be in the office most of that time on Wednesday. Thursday, I'm here 7:45 in the morning until 5:15, but please get everything into me before noon on Thursday. I think we have until noon on Friday to get the grades in, but I've got a treatment coming up Friday. I'll be there probably at 7 o'clock in the morning. I probably won't get away until 4:30 or so in the afternoon. Usually they take all day, and there's no way I'll be able to be on campus at all on Friday. So I need to get everything done before I leave at 5:15 on Thursday, and I'll be, so please try to get me everything by noon on Thursday. So I'll have time to grade it, averages and entered grades and stuff.
And what time is it tomorrow?
Tomorrow, I'll be here from 7:45 in the morning. I'll be in my office until a little before noon. I've got a test I'm giving up here. You can bring it up here between noon and 2, or 2-ish. It may not take them that long to finish. And then I'll be back in my office sometime after 2-ish until 5:15.
You said 7:45.
7:45 in the morning until around noonish. Okay, I've got a test that goes from noonish until 2-ish. And then I'll be back in the office from around 2-ish until 5:15. So except for the 12 to 2, noon to 2, I'll be up here the rest of the time in the office. Now I've got to run off campus for just briefly before noon tomorrow, but I won't be gone long. Okay. All right, any other questions before we get going? Okay. Now I can't return your research paper, but I have returned everything else that's been graded so far. And like I said, you wound up with, can't remember how many labs. It seems like it's going to wind up being 8 labs and 10 tests, because we did the 2 light chapters as 1 lab and these last 2 chapters as 1 lab. They're in 2 sheets, but they're 1 lab. All right, so let's pick up. We're on page, are any questions before we get going? On page 702, right at the end of 21.7, it's an application electric power transmission. And here is Brianna. All right. I've got a bunch of papers I can return to you, but I'll wait till at the end to do it. I returned them earlier, but I don't want to take class time to do it now. Okay, electrical power transmission. When you transmit electrical power over, and really that's energy, okay, over long distances, it is most economical to use very high voltage and as low a current as you can get away with, because the current minimizes the power loss. The power loss is in I squared R. The bigger your current, you square that, and you got lots of power loss. So if you can depress the current, increase the voltage, then that's the way to transmit the energy of the power of the wires. In practice, the voltage is stepped up to about 230,000 volts. Very high voltage, okay? At the generating station, step down to about 20,000 volts at the distribution station, and finally to 120 volts at your own utility pole. I don't know if any of you have done it, but when you're at home, look out, if you're in an apartment or house or whatever, look out at the power pole nearest your house, front, back, wherever it happens to be. You'll see a big roundish looking box there. That is your transformer that steps down from so many thousand volts to 120 volts. Okay? It's probably not 20,000 coming in. It's probably, a couple of thousand, because you've had other distribution sites that step it down before you got there. Okay? James Clerk Maxwell. It looks like it's Clerk, but it's really pronounced Clark. He was Scottish. They do strange things with the pronunciation. Lived 1831 to 1879. Only 68 years. Brilliant mind. Okay? Electricity and magnetism were originally thought to be completely unrelated from each other. Maxwell in 1865, that's over in Scotland, while we were just finishing up the war between the states, he provided a mathematical theory that showed a very close relationship between electric and magnetic phenomena. And these are called Maxwell's equations. And that's what 2.21.8 is talking about. Okay? He worked on the electromagnetic theory of light, which we now understand, kinetic theory of gases, nature of Saturn's rings. Okay, so he was an astronomer. Color vision, how in the world our eyes perceive and transmit color, and electromagnetic field interpretation, which led to Maxwell's equations. Okay, there is a picture in your text, by the way. I should have said this earlier. Example 21.7 is distributing power to a city, and there is a picture of that cylindrical step-down transformer that drops the voltage from around about 4,000 volts to the 240 that goes into your residence. Now, the slide here said 120. That's not true. It's really 240, because guess what? Every one of you's home or apartment or whatever has air conditioning, ovens, clothes dryers. Okay, you live out in the sticks somewhere, huh? Okay. All right. Those all run on 240s, not on 120. So it delivers 240 to your house, but then in your box, it breaks down, and some of it's 120 and some of it's 240. Okay? So, wherever that, I'm sorry, that was in the book. That is a picture of a transformer there. I guess that's the only page we got on Maxwell's equations. Maxwell's starting points. Okay? This is what you have at the bottom of page 703. Electric field lines originate on positive charges. Remember we did this before. Terminate on negative charges. Maxwell was the one that that was one of his starting points. Magnetic field lines always form closed loops. They do not begin or end anywhere. Okay? Part of that closed loop usually goes through your magnet, basically. A varying, and here's what we got. This is what we did in our labs. A varying magnetic field induces an EMF, and hence an electric field. So a varying magnetic field induces an electric field. That's Faraday's law. But magnetic fields are generated by moving charges or currents. That's Ampere's law. So basically, on the one hand, a varying magnetic field produces an electric field, and a varying electric field produces a magnetic field. This was the basis, and he built on that and came up with these equations. Okay, his predictions. He used those starting points and a corresponding mathematical framework to prove that electric and magnetic fields play symmetric roles in nature. Now, I don't know if I want to say symmetric or quasi-symmetric. They're not quite symmetric to each other, but awfully close. He hypothesized that the changing electric field would produce a magnetic field. Now, that had not been proven until probably 50 to 70 years after his death, and finally someone proved it. But he hypothesized it way before we had the technology to do it. Maxwell calculated the speed of light to be on the order of 3 times 10 to the 8 meters per second. We haven't improved on that much since. He concluded that visible light and all other electromagnetic waves consist of fluctuating electric fields and magnetic fields, with each varying field inducing the other. So one induces the other induces one, and that's how the waves travel through space. Okay? Pretty ingenious understanding of it by this long ago Scott. Well, that was Maxwell's prediction. Then came Heinrich Hertz, good German name. The first, he was 1857 to 1894. He only lived 37 years. Yeah. He was the first to generate and detect electromagnetic waves in a laboratory setting. He verified what Maxwell had predicted. Now let's go back and look at those dates again. He was born in 57. Maxwell died in 79. So, but you see, by the time 57 to 79, that's just 22 years. So about the time that Hertz was just coming into play, Maxwell was on his way out. Okay? Unfortunately, Hertz didn't live that much longer, but he did do quite a bit. He showed radio waves could be reflected, refracted, and diffracted. Now, we've talked about reflection and refraction in terms of light waves, but we haven't talked about diffraction that much. The unit Hertz, Hz, is named for Heinrich Hertz, Heinrich Rudolf Hertz. Now, why didn't they just name it H? Why didn't they use the unit H for Hertz?
Because hydrogen.
Because what? Hydrogen, yeah, that has a symbol that, but that's not the unit. Why didn't they use H for a unit?
Some other unit.
Yes, a Henry, which measures electromagnetic induction. The last chapter, Henry has just the H, so Hertz has to be Hz. And by the way, the Hertz is a very simple unit. It's a per second. That's it. 1 over second. A per second. Cycles per second. So here is Hertz's basic LC circuit. This is, what does L stand for? In an LC circuit? Inductor. That's the coil, inductor. Okay? C stands for?
The current. Yeah.
The what?
No. Which is current.
No, I stands for current. C stands for? Second? Parallel plate? Capacitor, exactly, a parallel plate capacitor. There it is, right there. Okay, when the switch is closed, oscillations occur in the current and in the charge on the capacitor. Okay? Now, wait a minute. Wait a minute. There's no voltage source here, is there? I sure don't see one. Here we have Shakita. By the way, for all of you who have come in since the beginning of class, I have your papers, or at least most of them, the ones that I've graded so far, are in the stack. I gave those out at the beginning of class, so you'll have to pick them up at the end of class, okay? Which will not be that much longer, okay? There's no voltage source there, okay? But let's just assume somehow there did get to be a voltage difference there. When the switch is closed, oscillations occur in the current and the charge on the capacitor. When the capacitor is fully charged, so I think you really need to have no, they don't even show it in the book. Yuck. A voltage source there. Maybe it's across the switch, I don't know. When the capacitor is fully charged, the total energy of the circuit is stored in the electric field on the capacitor. At that time, the current is 0 and no energy is stored in the conductor. Okay? However, when you open the switch then, okay, continue that, as the capacitor discharges, the energy stored in the electric field decreases At the same time, the current increases and the energy stored in the magnetic field, the inductor, also increases. When the capacitor is fully discharged, there's no energy stored in the electric field, but all of it is in the magnetic field of the inductor. The current is at a maximum and all the energy stored in the magnetic field in the inductor. The process repeats itself in the opposite direction. There is a continuous transfer of energy between the inductor and the capacitor. Okay? That's what happens, okay, in an LC circuit. And here's Hertz's experimental apparatus. An induction coil is connected to two large spheres forming a capacitor. Okay? So here's your induction coil here. The transmitter consists of two spherical electrodes connected to an induction coil, which provides the short voltage surges on the spheres down here, setting up oscillations in the discharge. Okay, so you have a strong electric field between these two charges here. Okay, then you have a receiver down here. The oscillations are initiated by short voltage pulses. That's why I said you have to have a voltage source somewhere there. And the inductor and capacitor form the transmitter. So that forms the transmitter. You have a receiver here with absolutely no power supply. It has two capacitors here that respond to what they sense here, and that then the receiver is a nearby loop of wire containing a second spark gap. Okay? And that's what is your receiver. So basically this is like a radio transmitter, a radio receiver, a telephone transmitter, telephone. Your telephone's the receiver. So you have these things, and we use these things all the time. Your TV remote, that's the transmitter. Your TV has a receiver. When you hit the thing there, it responds to it. We use this type of thing all over the place and never even think about it. Okay? So Hertz experiment, several meters away from the transmitter is the receiver. Think of your television remote. You know, you can do that from sitting across the room, several meters away. Your radio transmitter, you may be miles away. You could be kilometers away from that. This is consisted of a single loop of wire connecting the two spheres. If it had its own effective, I think inductance, not effect inductance, that doesn't make sense. Capacitance and natural frequency of oscillation. That's what the receiver has. When the resonance frequency of the transmitter and receiver are matched, the energy transfer occurs between them. I guess it's okay. It just seems like he's in present tense up there, he puts it in past tense down there. It's just a fairly poorly done slide. Okay? Hertz's conclusion, he hypothesized the energy transfer was in the form of waves. These are now known to be electromagnetic waves. The stuff that Maxwell had predicted almost, decades before this. Okay? Hertz confirmed Maxwell's theory by showing the waves existed and had all the properties of light waves. They had different frequencies and wavelength from light waves. That was the only difference. Speeds and everything else was the same. He measured the speed of these waves. Hertz measured the speed of the waves from the transmitter. He used the waves to form an interference pattern, calculated the wavelength, and here is the basic formula here. V, velocity, which is in meters per second. Meters would be your wavelength. Per second is your frequency. That would be in hertz per second. So V is found if you know the product of the frequency times the wavelength. V was very close to that 3 times 10 to the 8 meters per second, known as the speed of light. This provided evidence in support of Maxwell's theory. And Maxwell did not have the technology to test this. All this was in his brain, that it should work this way, and I've never known of a theory that from beginning to end worked much more perfectly than his did. Maxwell's equations are just absolutely beautiful in the fact they fit exactly what the theory, they present the theory very nicely, and everything they've done to confirm that has been confirmed really well. All right, Megan's here. Okay. So, when a charged particle undergoes an acceleration, okay, a charged particle accelerates. It has to radiate energy. Acceleration, there has to be a net force there. That net force reduces its energy. If currents in an AC circuit change rapidly, some energy is lost in the form of electromagnetic waves. Electromagnetic waves are radiated by any circuit carrying alternating current. Any circuit carrying alternating current. Okay? And alternating voltage applied to the wires of an antenna forces the electric charges in the antenna to oscillate. If you put an alternating voltage on an antenna, it forces those charges to move. When they move, they send out an electromagnetic signal. Okay? Waves. This is what the television stations are doing. This is what the radio stations are doing. This is what your microwave towers are doing. This is what, now some of those are just catching it and retransmitting. The electromagnetic waves by an antenna. Here you have a generator. That symbol means you're not a direct current, but alternating current. It sets up an electric field in that direction. You got positive charges there, negative charges here. Okay? The two rods are connected to an AC source. The charges oscillate between the rods. They start positive up there, negative down here. Later they go through a oscillation here. They're actually 0, 0. And here they're positive on the bottom, negative on top. Okay? So this is when they're starting. The electric field is down here. This is where they're 0. This is where the electric field is pointing upward. So it's here, going to down here, like this is. And then this is another wave length down the way. As the oscillations continue, the rods become less charged, that's B. The field near the charges decreases. The field produced at T0 moves away from the rods. That's what you have at B. So actually, they've got this moving this direction. The wave is moving here. What you've got now is here. Then they move this way, and that's what this is. And then when they change again, it goes back to 0 and then down here again. So they skip this step in here, but it's still there. Okay? The charges in the fields reverse in C, and they continue in reverse again in D, and then they'll do it again. Every time they reverse, it changes. Now this is electric field, not magnetic. Okay, we'll see what's happening magnetic in just a bit. Okay? So this is 2110, production of electromagnetic waves by an antenna. This is the figure you see near the bottom of page 706. Because the oscillating charges in the rod produce a current, there is also a magnetic field generated. Anytime you have a moving charge, you induce a magnetic field. The charges are changing, therefore a magnetic field is induced. As the current changes, magnetic field spreads out from the antenna. The magnetic field is perpendicular to the electric field. If electric field is going in this direction, magnetic field in that direction. But off by 90 degrees, okay? The charges in the field The stationary charges produce only electric fields. Charges in uniform motion, constant velocity, produce electric and magnetic fields. Charges that are accelerated produce electric and magnetic fields and electromagnetic waves. An accelerating charge radiates energy. There's the key. Now, a changing magnetic field produces an electric field. A changing electric field produces a magnetic field. Those fields are in phase, and at any point, both fields reach their maximum value at the same time. Now, that's how they illustrate it. Frankly, I understand it the other way. And it's my little bone to pick with them. But we'll go with this, okay? That's how they say it. The electromagnetic waves are transverse waves. The electric field's going one way, the magnetic field going the other way, and they show them in phase. And I'll leave it alone. The EM fields are perpendicular to each other. Both fields are perpendicular to the direction of motion, which is in the direction of C there. Therefore, EM waves are transverse waves. The E and M are doing like this, whereas the wave is doing like that. It's sort of like a three-dimensional shaking the hose on the ground, okay? Electric and magnetic fields are sinusoidal and perpendicular to each other. Both fields are perpendicular to the direction of the wave propagation, which is this way. Okay. Now, I'll have to agree with this and buy it because they say it and these people are more knowledgeable than I am. But my understanding has always was that it's the change in the electric field that maximizes the magnetic field. So to me, this should be shifted 90 degrees this way because when the change is at the max, that's when I thought the magnetic field was at the max. Not when this was at the max, but when the change was at the max. And similarly, when the change is at the max of magnetic field, that should be the maximum or minimum of the magnetic field. But they draw it this way, and they persist in drawing it that way, so I have to think they know what they're talking about, but it's not how I've always understood it. Okay? So what are some properties of these electromagnetic waves? We're into 2111 now. Electromagnetic waves are transverse waves. We've already established that. Electric field going like this, magnetic field going like that, the waves going perpendicular to both of those. The electromagnetic waves travel at the speed of light. And you get that by C is equal to 1 over the square root of mu naught E naught. Now, epsilon naught. I don't know if you remember what those were. If you don't, I think it's probably in the back inside cover, but I always go to front first just to make sure. No, those are conversion factors. So it's the back of the book. Go to your back of your book on the physical constants. The mu naught, the permeability of free space, 1.26 times 10 to the minus 6. That's Tesla meter per amp. And the permittivity of free space is epsilon naught, and that is 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. Okay? If you multiply those two together, that gives you something on the order of let's just say 10 is almost 9, well, more than 10, maybe about 15 or so, times 10 to the minus 18th. Take a square root of that, and you got something that's 10 to the minus 9, but 1 over that, and then that would give you 10 to the positive 8 when you flip it over. Because electromagnetic waves travel at the speed that is precisely the speed of light, light is an electromagnetic wave. So if you got a calculator, enter this for me, okay? 1.26 times 10 to the minus 6. 1.26 times 10 to the minus 6. That's in scientific notation. Is anyone doing that? What's that? Does anyone have a calculator that will do it? 1.26 times 10 to the minus 6. There's the EE or EXP key. 1.26 times 10 to the minus 6. Whoa. Wait. Okay. This is, let me get my pen changed. There we go. All right. I swear this thing is so tight, tangled up and everything. So this will be 1 over the square root of 1.26 times 10 to the minus 6 times 8.85 times 10 to the negative 21st. No, negative 12th. I'm sorry, I can't read. Dyslexic here. 10 to the minus 12. Okay. Now we won't worry with units right now, but someone do that calculation. 1 over the square root of 1.26 EE or EXB minus 6 times 8.85 EE EXB minus 12. Close parentheses for the multiplication, close parentheses for the square root, and for the 1 over 2. I don't know how many close square roots. What do you get? Got a calculator?
0.000007024.
Okay. When you multiplied those, did you take a square root too? Okay. One over the square root of 1.26 times 10 to the minus 6 times 8.85 times 10 to the minus 12.
I got a big number.
What is it?
It's like 2 something.
It's like what?
29946.
Okay, yeah. That sounds good. Say it again. 29946
294.
294.
5.6.
5.6. Okay? If you move the decimal 1, 2, 3, 4, 5, 6, 7, 8, that's very close to 3.0 times 10 to the 8th meters. Guess what that is? The speed of light. No wonder it's a big number. So you see that is indeed C, the speed of light, which here they list as 3.00, so they actually rounded one more. Okay. Now, because electromagnetic waves travel at the speed that's, okay, we already said that, I think. The ratio of the electric field to the magnetic field is equal to the speed of light. That's interesting, isn't it? The ratio of the electric field to the magnetic field is equal to the speed of light. The electromagnetic waves carry energy as they travel through space, and that energy can be transferred to objects placed in their paths. Okay? We are in their paths. The Earth is. And that energy, it hits the Earth and is transferred to heat energy, to light energy, to a variety of other energies. Okay? Energy carried by electromagnetic waves is shared equally by the electric and magnetic fields. And the I is equal to E max times B max, that's the electric field max, times the magnetic field max, divided by 2 mu naught, that was the permeability of free space, which is E squared max divided by 2 mu naught C, which is equal to C times 2 mu naught times B max squared. The intensity I is the average power per unit area, and that's usually measured in, I think it's Webers per square meter. I believe that's the unit they use for intensity. Let's see if that's listed here. Oh, let's go back a slide. The one you calculated, 2.9946, they got 2.99792. But we only input 3 significant digits. If you input more, then you actually get more digits out. They use 8.854919 times 10 to the minus 12, and mu naught was 4 pi times 10 to the minus 7. Okay, so you use those, you would probably get more significant digits. Okay. Now, the last on the properties of electromagnetic waves. Electromagnetic waves transport linear momentum as well as energy. For complete absorption of energy, that electromagnetic energy mu, P is equal to mu over C. Okay? For complete reflection of energy, then you have of the energy U would be P over 2U divided by C, because it goes in and comes out. Radiation pressures can be determined experimentally. How much, and this is true, how much that radiation is hitting on, say, our atmosphere, and how much pressure that exerts on the atmosphere and us as a planet as well. Okay? Now, how do we do radiation pressure? This is this figure at the bottom of page 708, figure 2122. This is the apparatus for measuring radiation pressure. In practice, the system is contained in a vacuum. There's no such thing as a perfect vacuum, but as much as we can get. In practice, the pressure is determined by the angle at which the equilibrium occurs. So, what we have here is a black disc here and a mirror here. And light coming in from one end hits the mirror, and this has no input or output, so the amount of twisting force that you have there, the pressure is determined by the angle at which that equilibrium occurs and is established. Pretty nifty looking thing, very, very sensitive. So what are your properties of electromagnetic waves? It seems like we've talked about these several times. Number one, they travel at the speed of light. Transverse waves, because the electromagnetic fields are perpendicular to the direction of propagation of the waves and to each other. the ratio of electric field to the magnetic field in an EM wave equals the speed of light, and electromagnetic waves carry both energy and momentum, which can be delivered to a surface. Okay. Interesting picture on, okay, there's applying physics 21.3, a solar system dust. That's an interesting thing to read and to try to follow. Followed by a quick quiz. Here's a quick quiz. In an apparatus such as the one in figure 2122, that's that one, suppose the black disk is replaced by one with half the radius. Which of the following are different after the disk is replaced? Radiation pressure on the disk, the radiation force on the disk, or the radiation momentum delivered to the disk in a given time interval. And it says which of the following are different. So you expect there to be two or maybe all three different. Any ideas? Okay, I think I'll just go to the back rather than guess on this one. This is 21.7. B and C. Okay? Not the radiation pressure on the disk, but the radiation force on the disk and the radiation momentum delivered to the disk. But then the one I was looking at was example 21.8, a hot tin roof, solar-powered homes. This home, its entire roof area is covered with solar cells, okay? And supposedly it is pretty much energy independent. All right. 2112, spectrum of electromagnetic waves. My word, this is a long chapter. We're almost at the end, though. Forms of electromagnetic waves exist that are distinguished by their frequencies and wavelengths. Okay? Now, all electromagnetic waves, whatever the frequency is, when you multiply it by their wavelength, you're going to get the speed of light. Because all electromagnetic waves travel at the speed of light. So you know that formula is going to be true. That's a given. That's a norm. So if you don't know one, you can calculate the other. Wavelengths for visible light range from 400 nanometers to 700 nanometers, which then would give you what the frequencies range. There is no sharp division between one kind of electromagnetic wave and the next. It's not like all of a sudden this was an X-ray, but then it became a ultraviolet ray. No. It's a very gradual spectrum, and they move very gradually from one to another. We put the names on them, and we put the sort of artificial limits on them. They really don't have those, okay? So here's the electromagnetic spectrum. I think this is on page, 712. So before we turn there, let's look at Quick Quiz 21.8. Which of the following statements are true, notice the R, so it's probably more than one, about light waves? Number A, or letter A. The higher the frequency, the longer the wavelength. True or false? The higher the frequency, the longer the wavelength. True or false?
True.
No, false, because look at this. This is constant. If you increase the wavelength, you have to decrease the frequency. If you decrease the wavelength, you have to increase the frequency, so you cannot increase both of them. You can't go to a higher frequency and have a longer wavelength. So A is not true. B, The lower the frequency, the longer the wavelength. True or false?
True.
True, that is true. C, so B is true. C, higher frequency light travels faster than the lower frequency light. True or false?
False.
False. They all travel at the speed of light. They don't have different speeds. Light has the same speed. So B's the only one true so far. D, the shorter the wavelength, the higher the frequency. True or false?
That's false.
No, that's true. Shorter wavelength, higher frequency. One goes up, the other goes down. So B and D are true. The lower the frequency, the shorter the wavelength.
Oh, there's a question.
The shorter the wavelength, the lower the wavelength, the shorter the, no. The lower the frequency, the shorter the wavelength.
True.
No, that's false, because you can't go, if one of them goes up, the other goes down. If one goes down, the other goes up. So only B and D should be true on that one. And sure enough, it's B and D. Okay. So let's now look at this spectrum. Okay, and again, remember, no sharp boundaries. We kind of impose these words on them. There is an overlap in the types of rays. Okay, waves. Gamma waves are very high frequency, extraordinarily small wavelength. Very penetrating, very deadly. Tissue cannot stand gamma rays, okay, in high doses anyway. Okay? X-rays overlap with gamma rays, pretty broad spectrum, and they also overlap with ultraviolet rays. So the X-rays that you get when you go into the dentist or you break a bone or something like that, those X-rays, the higher frequency of them, they're about the same as gamma rays. The lower ones are about the same as ultraviolet rays. Okay, the ultraviolet rays are here. And then look at the little bitty visible spectrum. What has happened to all these? Why don't we have these in the visible spectrum? Thank goodness our atmosphere blocks out most of the gamma rays, most of the X-rays, and a good number of the ultraviolet rays. How do we know the ultraviolet rays do make it through our atmosphere? Anybody? How do we know that ultraviolet waves do make it through our atmosphere?
Sunburn.
We get sunburned, exactly. We wouldn't get sunburned just by visible light. It has to be ultraviolet, so those do. That's why we get cataracts. That's why we wrinkle as we get older. These ultraviolet rays are the ones that age us, okay, and destroy us, basically. Now, below the visible light is a very narrow little band there. Below that, we get infrared rays, okay? Infrared are basically associated with heat rays. When the frequency goes down, the wavelength goes up, that's where you get heat. That's why, if you would go into the cab of my vehicle out there, I left the windows cracked so it would minimize this, but in the middle of the day, that light rays, the visible light in here, comes through and goes through the glass of the windshield, and then that takes away a little bit of the energy, which lowers the frequency, and lengthens the wavelength. Now those rays can't get out. That's your infrared. That's called the greenhouse effect. That's what a greenhouse does. The light rays go in, change the heat, that heats the greenhouse, and they can't escape again. That's what happens in cars. That's why babies left in cars or animals left in cars in the summertime when the windows rolled up, they die or they get very sick because the temperature in there can get very, very hot. Now, overlapping with infrared radiation are microwaves, okay? And then microwaves in just about where TV and FM radio waves begin. The radio waves, by the way, overlap with microwaves and overlap with the long wavelength waves down here too. AM radios are down here. In between there, we have a spectrum that I think, I'm not sure, but I think this is a spectrum that's being used by, I think that range might be being used by the internet, you know, I'm not certain on that. You have to check on that. But the types, visible light is only a very tiny portion. The other types are distinguished by frequency or wavelength. They all travel at very close to the speed of light. Frequency goes up, the wavelength goes down. Frequency goes down, the wavelength goes up. That relationship is always there. And here's the visible light expanded. We call this right below violet. Is right below ultraviolet is violet, then blue, then green. Okay. Now, some people put in the word indigo there. Indigo is just another form of blue or violet. So they put it in so you can have a pronounceable thing. Roy G. Bibb. There really isn't, well, I guess there is a color called indigo, but it's hardly distinguishable between blue and violet. Okay? They just put that in so you can say it. The shortest wavelength of violet is at 400 nanometers. The longest red is about 700 nanometers. These are approximate numbers. And anything shorter than 400, you get the ultraviolet. Anything longer than 700, you get the okay. Some more notes on the EM spectrum, electromagnetic spectrum. The radio waves. These are used in radio and television communication systems. Microwaves, wavelengths from about 1 millimeter to 30 centimeters, are well suited for radar systems, like when you're tracking planes or ships or other things. Microwave ovens are another application of microwaves. They're fairly long wavelength, 1 millimeter to 30 centimeters. That's a pretty big span there. Fairly low frequency, which makes them fairly low energy as well. Infrared rays are incorrectly called heat waves. I just incorrectly called them. They're produced by hot objects and molecules. The wavelengths range from about 1 millimeter to 700 nanometers. That goes right up into the red visible light. Readily absorbed by most materials. Visible light, part of the spectrum, is detected by the human eye. The wavelength ranges from 400 nanometers to 700 nanometers. Those are approximate. Most sensitive are about the 560 nanometers to our eyes, visible, you know, that's in the yellow-green. Okay, right about the middle of it. Ultraviolet light covers from 400 nanometers, violet, up to about 0.6 of a nanometers. The sun is an important source of ultraviolet light. Most UV light from the sun is absorbed by our stratosphere, in the stratosphere by the ozone in that stratosphere. By the way, on that topic, do you remember what freon is? Anyone ever heard of freon?
Don't you put that in your car?
What's that?
Don't you put it in your car?
This will makes air conditioners work.
Okay.
Yeah, you put it.
It's a gas that is nicely compressible, gives off lots of heat, it expands, it cools things. Was a fantastic gas. But the original freon, do they use that anymore?
No.
Why not? It destroys the ozone. And if you destroy the ozone, more UV light gets to the planet. More UV light gets here, we die sooner. We age faster. We get cataracts more easily. We sunburn. We get cancers, skin cancers, other cancers. So yeah, we didn't like that. And when they found that out, I think these are called the CFCs, chlorinated fluorocarbons. Those were the bad things in the original, what did I just call them? Not working well. Freon. Now they have other refrigerants that don't destroy the ozone. Thank you very much. X-rays. Wavelengths range from about 10 nanometers to about 10 to the minus 4th nanometers. The most common source is the acceleration of high-energy electrons striking a metal target. We manufacture those, used as a diagnostic tool in medicine. X-rays are used to look at bones to see if you have breaks or sprains or weak bones, as in could have bone cancer. Also teeth. The dentist uses X-ray to detect cavities and things within your teeth that you might not be able to see without it. Very much a diagnostic tool. Gamma rays. Wavelengths from 10 to the minus 10th meters to 10 to the minus 4th meters. Extraordinarily short wavelength, very high energy because they have high frequency. Emitted by a radioactive nuclei, highly penetrating, they cause serious damage when absorbed by living tissue, as in they kill living tissue. Looking at objects in different portions of the spectrum can produce different information. Now, when we did the atomic bombs on Hiroshima and Nagasaki, most of the deaths a lot of them were trained. People died from just the heat. I mean, that burned them to a crisp. But the people that survived the heat, many of them died because they were exposed to excessive gamma radiation. So it's not good stuff at all. That's why those astronauts out there in space, they've got to have those flight suits on reflecting that harmful gamma radiation. If they got exposed to it, they're toast pretty quickly. I mean, it's not quick. It's a long, slow, lingering death. Remember, the Russians poisoned one of their own operators who they thought was going to turn. They poisoned him with a high gamma radiation dose of stuff, put it in his coffee or his drink or something. He suffered a long, slow, but certain death. Pretty bad. Here are what they call crab nebula, okay? The X-ray image shows you the X-ray portions of that. Now in my book, on my screen it looks blue, but in the book and on here it looks purplish. The B is the optical image. C is infrared image. This is the same nebula. And D is a radio image, which is sort of fuzzy looking to me. 2113. I think this is the last. Doppler effect and electromagnetic waves. Remember what the Doppler effect is? What's the illustration of the Doppler effect?
The sirens?
Yes, when a siren is coming toward you, it's going up in frequency. When it's going away, it's going down in frequency. It's going at the same frequency. It's our perception of it. That's because it's piling the wavelengths together or spreading them apart. The Doppler effect occurs in electromagnetic waves, but differs from that of sound waves. For sound waves, the motion relative to the medium is most important. For light waves, the medium plays no role, since the light waves do not require a medium for propagation. The speed of sound depends on the frame of reference. The speed of electromagnetic radiations is the same in all coordinate systems that are at rest or moving with a constant velocity with respect to each other. So you don't get a change of speed, which you do with sound waves. You don't with electromagnetic radiation because it all travels at the speed of light. It doesn't change speed. Here's the Doppler equation for electromagnetic radiation. It's FO is the observed frequency that you are sensing. F sub S is the actual emitted source frequency emitted from the source, and that's 1 plus or minus U over C, where U is the relative speed of the source and the observer, and the equation is valid only when U is much smaller than C. You cannot get U close to C. It just doesn't happen. It's only valid when U is much, much smaller than C. And it only changes the frequency, which would change the wavelength, but doesn't change the speed at all. Okay? The positive sign is used when the object and the sources are moving toward each other, negative sign when they're moving away from each other. Astronomers refer to a redshift when objects are moving away from the Earth, since the wavelengths are shifted toward the red end of the spectrum. They're getting longer because they're moving away. Okay? And that's all, folks. That's the end of Chapter 21. That's it for us. The summary here, 21.1 has a few definitions, one formula, two formulas, some illustrations. Okay? 21.2, capacitors in an AC circuit. Again, you have a couple of equations, a couple of definitions, and a figure. Inductors in an AC circuit. Again, we have some definitions, a couple of equations, or one equation and a figure. No, a couple of equations and a figure. 21.4, RLC circuit, resistor, inductor, and capacitor. Several illustrations there, several equations, and one of those introduces the concept of impedance and phase angle. 21.5, power in an AC circuit, one equation, a couple of definitions. 21.6, a couple of equations, one or two definitions. Transformer, two equations, nice figure, explanation. 21.8 to 21.13, lumping all those together, several equations, a couple figures, several big bullet points. Conceptual questions, the odd answers are in the back. You can do any of those odds that you would like. Those are good to feel through what's going on, good for building concept. The problems, though, are much more like what you'll see on your test. On 21.1, any of the odds 1 through 5 would be appropriate. 21.2, any of the odds 7 through 11 would be good. 21.3, any of the odds 13 through 17. 21.4, any of the odds 19 through 29. 21.5, any of the odds 31 through 35. And 21.6, any of the odds 37 to 41. Transformer odds 43 to 47. And 21.10 and 11, 49 through 57. 21.12, any of the odds 59 through 63. 21.13, any of the odds, well, do 65. That's about it for that. Additional problems, not as many because there were so many of the others, but any of the odds 67 and 75. That's it, folks. That gets us to reflection and refraction, which we've already done. So we have pretty much finished. We didn't do as much on the modern physics, relativity type stuff, because I needed to get labs and tests to FA, who had to leave early, and I didn't have time to do it, so that's why we went back and picked up these. So, with that said, we're through with the That's all the material we're going to cover. Now, this would be a very good time for you to check and make sure you've done everything that you needed to. These are the ones that were turned in. All right. I'm going to turn off the projector and give you the lab and your test. You can work on those in any order you want to.
I have a question.
Yes.
I had what you gave out last week.
What's that?
What did you give out last week?
I don't remember all of what I gave out last week. It's what have you done? You know.
It was test 8, I know that, and then
Okay.
you said last week's lab was part 1, and this week, or today's lab was part 2, they're gonna combine to do one lab, correct?
Exactly.
So can I have test 8 and part?
Okay. Well, let me start over. In 202. Okay. Now I'm still recording. Do you think any of you? I'm going to pause this so we don't have to record this. Pause the difference until tonight. The only one I have an extra copy of is the one that's numbered 1 through 14. Okay. So if you got that one, good. If you got the other one, I've already done it. It's equivalent. May not be exactly the same questions, but it's equivalent. So if you want this one, I can make another copy of this if you want to do this in addition to what you've already done. But if you want to turn that one in, you certainly can. But I don't have another copy of the one that's A, B, C, D, or whatever it is on that one. I only have the one that's numbered 1 through 14. That is the first half of the lab. I gave it out last week. Does anyone still need that?
So if you since you don't have the other half, what would you get a 0?
I'm going to give you the other half tonight. But what I'm saying is if you got this copy and you want to do it, that's fine. If you have the other one and you've already been working on it, it's equivalent to this one. That says it's Laboratory 6, Electromagnetic Induction. There are 2 different copies, but they're equivalent to each other. They may not be exactly the same, but they are equivalent. So, does anyone lack this? Does anyone need a copy of this one? Everybody? Oh, I thought you had. Oh, you want?
Well, I have the ABC. I want the one that everybody else has.
Okay. Does anyone else want this one?
Yeah. I don't think that one saying yeah. Yeah, I don't want that.
Well, I mean, we kind of want to drop it, but it's okay. We'll.
If we drop the one from last week, we're gonna do the one tonight, right?
Okay.
They're the same.
Those are
It's the
2
same.
halves of the same lab.
So it can be the one I drop.
Yes.
You can
It's
drop
up to you.
last week and
If you
tonight.
don't, look, I'm going to drop your lowest lab score.
So that'd be
If
my
it's a
first
0, I'll drop a 0. If it's a 13, I'll drop a 13. If it's a 24, I'll drop the 24. Whatever your lowest lab score is, that's what I'll drop. If you have 2 zeros, one will be a 0, the other will be dropped. Okay? If you have a 13 and a 0, you'll drop the 0. Okay? So how many need a copy of this one that says 1 through 14?
Well, I guess I don't need it.
Yeah.
You don't?
I guess we don't.
That'll be my drop.
Yeah, that
Huh?
was our job.
Okay, well, it's up to you. It's completely up to you. Okay? Now, does anyone need a copy of this? That's what I'm asking.
No.
No. Okay. Does anyone need a copy of test 9? It says test 6 on the top. The first question is a uniform 4.5 Tesla magnetic field.
Isn't that the final?
No, it is
That's
not.
what he gave out
That's the
last
next to
week.
last test. That's what I gave out last week.
We all need that.
Okay? Shakina, you got one, didn't you?
Oh, would you drop it?
Effie did. They were here last week.
Oh, you want to, okay.
Okay, you need this?
No.
You got it?
Yeah.
Okay. You need it?
Part 2. Just give it to me.
This is test 9.
Okay.
Just
I won't have no 2 zeros and I'm
Right.
This is the final.
No,
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 this ain't
test
the
9.
final.
That's the one I gave out last week.
Oh no, I don't need it.
This ain't test 6. Did we scratch this out?
Test,
I don't need it.
you don't need it.
What is
He
it?
just said that.
Okay.
Okay.
I have a lot of extras of those. No one needs it.
No.
Okay.
Okay, so this
I see you.
All right. Now, the
That's just not.
second half,
So what is the point?
Test 10.
I'm handing it out tonight. This is one I handed out last week.
See?
Yes, you weren't here.
If it's
No,
testing-
this is what we're saying. Like,
Oh, the numbers are wrong on the
different.
sheet.
So the one from the 24th, 2 weeks ago, it says test 7. It's supposed to be 8.
Okay. Now, the test numbers are, yeah, they're off because the last time I taught this course from this book, they had a different order, okay? Now they changed the requirements for the course. But, okay. Lab 7 is the second half of this week's lab. How many of you need this?
I'm gonna drop it.
Okay, everybody gonna drop it? Okay, then your lowest lab score stays as your lowest lab score, then it won't be dropped. This will be your one and only drop. Okay? Okay, then the lab from tonight is, it says on the top test 7, but it's really test 10. What is the effective RMS current? Okay, and this is the one everybody is required to. You already have it. Right.
What did it say again?
What's the test?
Test what?
No, you don't have it. Oh, yeah, that's right. Yeah, that's right. So we have to finish the chapter. But are you sure you didn't get it when I gave it to you?
Yeah.
That's what I thought.
Yeah. I'm looking at it.
Yeah. I thought when I gave it to you. Okay. Have you got that? Okay.
This is the final.
Yeah.
Here's Sam.
Wait, thank you. That's what I thought was Sam, but whatever.
Oh, okay. They're all blank.
Okay.
And I need
And
one
that
more.
was the
We need one more.
fourth one, so let me go make a
Oh, so I
copy
will
of
take it.
This one's kind of hard.
No, here it is.
Oh, we found it.
I think so.
Okay, this is.
So what's the
Check the grouping.
Yeah,
I just changed the numbers.
okay,
For me and Tia.
okay.
Or Tia and I.
I didn't change the numbers on it, but
What's
you
that?
won't get confused. I didn't change the numbers.
Well, I know what the test questions are and which ones they
I'm
are.
gonna just put final test, final exam.
You can write that on there, you can write anything on there you want to.
Okay.
Right?
Pardon me?
Well, here you go.
Okay, let's see if there's anything. Okay, did everyone get a copy of, this is the one we had from chapter 22, I believe it was, 21 or 22. It was on light, the nature of light. Because I have one extra, that's probably the woman who's not been here, that's probably her. So y'all probably all got copies of that, okay? And then the next test 8 was how large should a wall-mounted mirror be? I passed this out last week. Did y'all get this one? How large should a wall-mounted mirror be? This was from chapter 20, I think it's 22. Everybody's been turning in so much, I don't know what you turn in. We had two on light, 22 and 23. 22 was a test that started according to the photon energy formula. That's the first question on it. That was from chapter 22. And the one from 23 started, how large should a wall-mounted mirror be? Did all of you do both of those? I have extras. I don't know why I have extras.
What does it look like?
Yeah, I guess it's a list.
That's what I'm telling you. How large should a wall-mounted?
That's
Is it
test
la- is
eight.
it a last-
That's
It's
what we
test
got
8.
Wait, no,
That's
the
test-
first thing this is according to the full time.
Okay,
That's
yeah.
the one from.
That's the one from
week.
chapter
That's the
22.
week before last.
And then 23,
You must do what last week.
23, hardly anyone got it because you weren't here that night. So, do you need is test 8, how large should a wall-mounted mirror be?
Test 8 is what I just turned into you.
Okay?
Test 9 is a uniform 4.510 magnetic field pattern.
Shakina turned in this one.
That was one from last week.
Yeah.
Last week, that was test 9,
Yeah.
but it says test 8 at the top of it.
No, it don't. It says test 6.
Okay. This one, according to the photon, okay,
That's test 8.
yeah, well, that's listed as test 7. The one that's listed as test 8 is how large should a wall-mounted mirror be?
Nobody has that.
Well, some people have,
That's
because
the
I've
one
had
that
them
was
turned in.
dropped, the one from last week.
Yeah.
No, it's not. That's not.
This is the one from last week. It says uniform.
We had 2 last week.
Okay. Y'all into the test?
Yes.
Oh, well, that makes more sense then. We were so
Y'all
confused.
Okay, well, can you
Why
make
y'all
that?
got 2 tests? I'm confused.
Well, we finished the chapter and she hadn't run off the test yet. And I couldn't get it to you.
So we have to do test 9. Because you drop it.
Okay. Does anyone else need a how large?
Yeah.
Okay.
Dang.
Well, that's why you should be here.
I'm not saying dang to you.
Okay.
I'm just gonna wait till it comes down.
What's
I was
that?
just gonna ask to see mine back. I wanted to make sure that it is.
There's your how large should it be.
Okay, so this is from last week. I'm trying to make sure that I turn in the other test 8 though.
What's that? This is the final.
Okay.
So technically,
Okay.
the final is test 11.
That's
No,
That
test-
was the one before the
this
final.
is test 9.
this is what test.
Or one of
Okay.
the tests from last
The
week
numbers
is
are
9.
just screwed.
Yeah.
From now on, I'm gonna put the chapter numbers on top.
That'll make so much better.
No, the final's 10.
It's 2, they got 2 tests last week. I just turned in test 8.
We were on 6 the week before. No. Did you turn yours in? So do you want to have this one or this one?
I'm so confused where that one came from.
A uniform.
Okay. All right, are there any more questions? Should I leave this running or should I start uploading?
You should start uploading.
Okay.